Yeah, hi, so I'm Uli Fahrenberg. I'm handicapped because until yesterday I thought it was perfectly acceptable to give a Blackboard talk here, or at worst a whiteboard talk, so I have no slides, right? So the title of my talk is rather long, so I'm only going to give you the short version. It's two cats with Lax Tensors. The actual title has an extension, which is motivation from concurrency theory. So I'm here to talk also about concurrency theory, or more precisely and maybe less nicely what people sometimes have called true concurrency. So I'm interested in worlds where I can make a difference between things which happen at the same time. I know I don't need those actually. So this is I'm also not very good at drawing at those things. So yeah, please bear over with me. So if you know Petri nets, then this will be a very simple Petri net which can do A and B independently, right? So you have an A transition, you have a B transition, and they can happen independently. Now, if I add an extra place and some arrows forth and back to the transitions, so let me see if I can draw the arrowheads also. Okay, that's not so bad. So now I've made A and B not independent anymore, right? So now A and B can happen in any order. I can either first do A and then I can do B, or I can do first B and then I can do A, but they cannot run in parallel anymore. And I want to make a difference between those two things. So for me, A parallel B is not the same thing as AB plus BA. You see? So this means that, let's say on the semantic side, on the side of languages, I cannot consider words anymore. I have to consider what I call as what I call pomset semantics. Does this ring any bells? Okay, so let me go. Ooh, this is nice. Thank you so much. So actually, this thing has been developed by my good colleague François Schwarzentruber in Rennes, and it's actually very nice. Sorry. Here? Ooh, it gives. Oh là 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 là, il est vraiment fort, François. So I'm in a setting where things that happen, they can happen concurrently and they have a duration, right? So for example, one thing which I would like to be able to express is that I have an event A, which happens before an event B. And while A is going on, there is an event C which is starting, which is continuing while A is stopped, when A is stopped. And when B is starting, C is still running. And then C is stopping while B is running, and an event D is starting, right? This would be something which you would like to express in this world of non-interleaving concurrency. So how does it look as a well, it's not a word, right? I cannot say. I mean, I don't know the. I mean, it's not just ABCD. It's not just ACBD. It's something different, right? It's if it is something, it's many different words. So I could take all the linearizations of this thing, right? So what would they be? Well, all strings of A, B, C, D, where the A comes before the B and the C comes before the D, right? This is all the words which are in the semantic of this system, right? And instead, I want to use partially ordered words as semantics. So I want to say, well, the A comes before the B, the C comes before the D, and also you notice that the A comes actually before the D. Right? So this is called a pomset, a partially ordered multiset. It's a generalization of words which people have been using for a long time. It's been invented well, as Petri net semantics, essentially, right? When you go back, I don't know, Winskill, other people, event structures. This is where those things come from. And what I'm interested in is the algebraic theory of those things. And then when you go and look for the algebraic theory of those things, you note that, well, okay, those things have two compositions, right? So words, I can concatenate them. So those pomsets, I can also concatenate them. What does it mean to concatenate two pomsets? So I'm not drawing the labels now, I'm just drawing two of those, let's say, N-shaped structures. So what does it mean to concatenate them? It means that everything which is on the left comes before everything which is on the right. So concatenation means I'm adding precedence arrows like this. Right, so now I know that everything on the left precedes everything on the right. Yes?
Sorry, maybe this is a silly question, but where does the multi-set come into this?
The multi of multiset comes in because this C might be an A. Right? So now you have an A which is running in parallel with another A.
Oh, okay.
Right? So it's there is in this world there is a distinction between events and actions. So in this setting now with two A's, you have two events which are distinct but which have the same label, right? So the same thing happens twice. Right? Another setting could be that I don't know, you have three researchers between you don't want to distinguish, so it's just three things, three researchers and two printers, and you also don't want to distinguish the printers. But you would like to express the situation that any two of those researchers can print at the same time, but not three of them at the same time, right? So then you just have a multiset, a partially ordered multiset of three things, which are the same.
So you want to think of the two A's as sort of being the same, but
as being the same observation, right? Not the same thing happening, but the same observable event. The same observation. I shouldn't say event. I should really say observation. The same action. Yeah. Okay. Thank you for the question. Okay, so this is what is called serial composition of pomsets. And of course, you can also put them in parallel. So what happens if I put pomsets in parallel? So this is easy. If I have a pomset like this, and I have another one, which is maybe, I don't know, and getting something N-shaped, well, putting them in parallel is just putting them on top of each other. Right? It's just a disjoint product of directed graphs, basically. Yes?
Can you kind of shortly give the description? What does it mean to be a like ordered or partially ordered multiset? Like,
It's
I get the intuition. What's the formalism?
Okay, let me just write it here. It's a partial order together with a labeling from your events to some set of actions, which is usually called sigma. Right? So now if you want to consider words, then your partial order here will be a total order. Right? A word is a totally ordered set with a labeling to sigma. Right? And then the only thing we are doing is to restrict to lift the totality of the order to a partial order. Okay. Afterwards, things are slightly more complicated because you would like to abstract from this from the names of those events, right? So you would you consider actually equivalence classes, you consider isomorphism classes of those things, but this is a technical thing which I'm not going to get much into here. So there is a formal difference between, let's say, labeled partially ordered sets and partially ordered multisets. Ooh, thank you. But we're not gonna do this much here. Okay, so now, so what do we have as an algebraic structure? So we have our set of pomsets. We have a serial composition or a concatenation. We have a parallel composition. Now, what are the units? Do they have any units, those things? Well, the unit for the serial composition is the empty pomset, which is also, funny enough, the unit for the parallel composition. Right? So I have those things have a common unit, which I'm just going to call 1. You might want to call it epsilon instead or something else, right? So what is this? Well, it's a bimonoid. It's a bimonoid where your serial composition is not necessarily commutative, but your parallel composition will be commutative, right? So it's two monoidal structures on S, one of them commutative, the other one not. Are there any interactions between those things, between those two operations? Well, the funny thing is, yes, but you don't see them right here. Because, so you would think maybe, okay, if I have two structures, I mean, this is a category conference, there should be maybe an interchange law or something like this between the two, right? There is none, but something funny happens. If you think of, so this example has not much to do with the other one, even though the events are called the same. So here on the left, I'm putting A in parallel with C, and then I'm concatenating it with B in parallel with D. And on the right, I'm putting A before B, and then I'm putting those in parallel with C before D. And now you see that there is more order on the right than on the left, right? Those things are related in some strange way, because on the right, everything in A happens before everything in B, like on the left. Everything in C happens before everything in D, like on the left. But also there are some extra arrows between A and D, which you don't see on the left. So this is called subsumption of pomsets. This is a partial order on pomsets, which basically means that the thing on, oh, did I? I think I made a mistake. I would have liked to be more order on the left than on the right, right? So there is more order on the left than on the right because A is before D on the left, and C is before B on the left, right? And on the right, this is not the case because C and B are partially concurrent. I'm sorry for this. Have I cleared up any confusion or introduced more than I have cleared up? It's okay, fine. So, okay, so I hope I have convinced you that on the left there is more order than on the right. This is called subsumption. This is also from the 80s, introduced by a Polish-German guy called Grabowski, an American called Gischer. Von Pratt was also in this business. Is there a question? Yes. Yes, it is the right one. So this subsumption means that there is a pomset morphism from right to left on top of the identity.
Is that just the refinement of the partial order?
Yes. This is refinement. Yes, subsumption is the inverse of refinement. Yes, yeah, exactly. So the actual structure you want to consider is not this, well, it's not just this bimonoid on top. So now I would like to see if I can remove this parentheses. Ooh. But a bimonoid with a partial order, which satisfies the Lax interchange law. So what precisely is the Lax interchange law? It's that if you take A parallel C, you put it before B parallel D, then you are below, well, AB parallel CD, right? This is the interchange law. I have an interchange between my two compositions, which is Lax. Okay, so this was the first part of my talk. I don't know how many parts there will be. This depends very much on the time I have. Last time I did this talk some weeks ago at IRIF, I took 2 hours. Yeah. Thank you. But please try to guide me in the timing because I have no access to a clock. Okay, thank you. So those are called concurrent monoids. They were introduced by Tony Hoare and Bernhard Müller and Peter O'Hearn and Georg Struth and other people in the early 2010s, with the motivation to so concurrent monoids, and on top of this concurrent Kleene algebra, to extend the success that Kleene algebra has shown in the non-concurrent world to the world of concurrent programming, right? And they have absolutely failed. So I recently talked, some weeks ago, I talked with Bernhard Müller, who told me, who complained that there are no applications of concurrent linear algebra. No real ones. I mean, they do have applications in their papers. They're always trying to invent things, but he was complaining that nobody has ever taken the bait and actually used it for something interesting. And I'm going to try to show you why. The problem is the free models of concurrent linear algebra. Have you heard of series parallel pomsets? So we said here we have, okay, here, I should point at this. There are two operations, right? There is a concatenation and a parallel composition. And now the next thing you would like to do is, what are the free models of my algebraic structure? And it's quite easy, because what can you do? I mean, for what is the first candidate for the free models? Well, you take all your elements of sigma, all your letters, all the singletons, right? And you see what you can construct using those two compositions from them. Right, so I don't know, you can construct A followed by B, you can construct A parallel B, you can construct A followed by B parallel C. And it turns out that one thing you cannot construct is the structure we saw already, which is this one. This one is called an N. It's called an N because people usually think of Hasse diagrams. Except we don't. For concurrency, people, left comes before right? Because concurrency is a Western European business. So for us, I don't know, it's more something else. But in any way, so this is an N, and the series parallel pomsets, so the free models for concurrent linear algebra, are precisely the pomsets which do not contain induced sub-Ns. So the N-free pomsets, which means that if I now can go back to what we had been writing in the beginning here, so this example of A followed by B in parallel with C followed by D, it's something I cannot model in concurrent linear algebra. Or I could maybe, I have difficulties, right? It's not algebraic. In a sense, concurrent linear algebra is not algebraic enough for, oh damn it, for what I want. This is no. All right, voila. So what can we do instead? Haha. So let me try to do this again. Voila. And now what happens if I know? Why is it doing this? Yes, please. And now this one. Well, okay, let's just go there. So, you know, I'm still adapting to this fancy technological world. What we did, so I should also say that this is joint work with my very good colleagues, Christian Johansen from Norway, Georg Strutt from Sheffield, and Krzysztof Ziemianski. That's a complicated Polish name, from Warsaw. So what we did was to equip pomsets with interfaces. So the idea is that you would like to say that things can continue across compositions. So we would, for example, like to say that if I have an A on the left, and I have a C, well, and I have another A on the right, that this is actually the same A. And if I compose those two things, what do I get? Well, I get one A, which started on the left, is continuing on the right, and I get two Bs. Right? So this is a sort of serial compositions where I'm allowing myself to continue things across the composition. This is inspired just a bit also by message sequence charts, if you know what those are, right? So those have compositions where processes can continue across compositions. So now we generalized, and I'm not gonna have time to give you the details on the precise definition either. So serial composition has now become a gluing composition of pomsets with interfaces. So now we look at pomsets. So let's take this N-shaped thing again, where, for example, I want to say that this A, it's not something that I was starting in this execution. It's something which must have been started before, right? So it can only compose on the left with another pomset where the A is still running, which is offering an A, right? And similarly, I could say that, well, I don't know, the D and maybe also the B are in the terminating interface, so that if I want to compose it with anything, it needs to be something which has a B and a D running. So formally, those so-called I-pomsets are sets with two partial orders, where one of them is the precedence order that you see here. Another one is a bookkeeping order, which allows me to properly compose things. And they form, so they don't form a double monoid, they form a category. Right, so you can easily imagine, I don't need to go into details at this conference here, that so if you have an IPOM set like this, it has a type, right? So yes. This is where you need the event order, right? This is where, so if I have an A followed by a B and a C followed by a B, like this, and both B's are in the interface, then I need to say, using my event order, that this B is the first and this one is the second, right? So it has no computational meaning, it's a bookkeeping order. And actually you need, what you really want is finite sets with two partial orders, so that any two elements are related by one of them. Right? So the union of the two partial orders of the precedence order and the dotted event order needs to be a total relation. This avoids having non-trivial automorphisms, for example, on your structures. It gives a very nice categorical structure and lets you do lots of interesting things. So those things form a category on the natural numbers. Well, maybe not on the natural numbers, actually on a, if you don't have labelings, it's on the natural numbers. If you have labelings, it's the category in sigma star. Right? So where sigma star is now not seen as words, but as parallel words. We call them concurrency list or conc lists in our latest paper. So you have a category where your IPOM sets are morphisms on objects sigma star. The gluing is your composition in this category. But then what about parallel composition? So parallel composition is of a type which looks like a tensor, right? So how do I say this properly? If I have a pomset P from an A to a B, and Q has interfaces C and D, then what is their parallel composition? Well, it's a new pomset PQ, which goes from AC to BD. Something like this, right? Where this is now concatenation of words in sigma star, except that I'm reading words vertically. So it also means that PQ cannot be the same anymore as Q parallel P, because the type will be different, right? Maybe they are structurally the same, but they have a different type, which means that when I compose them afterwards in gluing with other IPOM sets, I will get different results. So I've lost commutativity of parallel composition, which is something that all our reviewers at computer science conferences have complained about. And you know, people are trying to find solutions and stuff, and we've also tried to find solutions for years, and we've been I'm convinced that it's a good thing not to be commutative.
You don't have a morphism from AC to CA, for example?
It's there is some symmetries, but it's symmetries on another level, right? So you can compose. Well, no. If you are in this strict setting where you have event orders, there is no relation between P parallel Q and Q parallel P, right? Because the event order is going differently, is going the other way. So you have absolutely no, you have no morphism between the two. So I don't want to dwell too much with this. I just want to say, well, so it has the type of a tensor, right? But it's not a tensor because it doesn't satisfy interchange. So what does it satisfy instead? Well, there is a way to lift the Lax interchange law that you saw for concurrent Kleene algebra to a categorical setting. But of course, you need to take subsumptions into account. 5 minutes? Fine, thank you very much. I shall see if I can repair this. The subsumptions give you a two structure on your category of pomsets now, right? So now you have your strings, which are the objects. The pomsets are the morphisms, and then it may happen that you have two pomsets which have a subsumption between them. So subsumptions, I mean, I didn't give the formal definition or refinements, if you wish. They have to respect interfaces for this to work, which is a natural requirement. And then actually the interchange law becomes that the identity to morphism. Where are my notes now? Okay, I have notes, but I'm not using them for anything. So the identity from well, A parallel B, C concatenated with B parallel D to A B parallel CD is a subsumption, right? This is the interchange law. This is a theorem that the morphism over the identity from the concatenation of the parallel compositions to the parallel composition of the concatenations is a subsumption, which means that your parallel composition becomes a Lax tensor. Well, becomes something which should be called a Lax tensor, except that when we were at this stage, we asked people around what are Lax tensors, what are non-strict tensors, and we found nothing which looked like our Lax tensor. So this is hence the title of my talk. I believe we found a new notion of Lax tensor, which in the end is just a Lax and strictly unitive functor from the product of C2 itself, right? So the definition is, and let me finish with this then. A Lax tensor on a 2-cat C, okay, that's a very ugly C, is a Lax and strictly unital functor from C times C to C. This is what we get. This is what we need. This is the algebraic structure that generalizes concurrent Kleene algebra to a setting which we believe will actually be useful in applications. Thank you.
I'm bang on time, so we can take some questions.
Hi, nice talk.
Thank you.
When I saw this sort of idea of these two different kinds of composition with this Lax sort of interchange law, it reminded me of the notion of duodal category. Don't know whether you know much about duodal categories. But is there a connection there?
No, I don't. Okay, the answer is the no was to the first part of your question. I do not know much about duodal categories. I would like to know more about them. So I'm not a category theorist. I'm nothing. I'm not anything. I'm not a topologist. I'm not an automata theorist. I'm not a category. I'm in between everything. So please, yeah. Is this on NCAT? Duodal?
You should find it on the end.
Okay. Thank you. Yep.
Yeah, so similar question. I mean, this looks like this could be described as structured postbands.
Yeah. Yep. Yes.
Have you considered that?
So actually, you can define the gluing as a type of ordered push-out. Right? It's not a push-out on the nose because you also need the things on the left to come before the things on the right in the result, right? So there is some order on your. I could draw something if we have time for me to draw something. What you would want to say is that so if you have a pomset P which has a target interface, which has a source interface N, and another one which has a target, the other way around. So this is the source, the target of P is N and the source of Q is N, then you can compose them and the result should be a push out in one way or another, right? It's not directly because you want to add those arrows from elements in P which are not in the interface to elements in Q which are not in the interface, right? So there is some kind of ordered thing. It's some push-outs of ordered squares in some double category or something like this. I was trying to formalize this in one way, and then I asked the son about it, and he started about the pro-functors and their stuff, and lost me immediately, right? So.
You know that the comma category is like the dual of that. Yeah, it's a.
Yeah.
Yeah, it's a kind of a pullback, but you have this arrow in the middle, so it's a universal. But not exactly a pullback. You have this kind of arrow there. So this is kind of looks like a dual to comma category. So.
It looks like a dual to comma categories.
Yeah. Because so in comma category you have F down arrow G. You have forgetful functors, and then you continue with the functors, and then you have a natural transformation in the box, and in some sense it's a universal such. So it's a typical and it looks similar as that, but yeah, I'm not exactly sure what's.
We might need to continue this offline, but I would really like a reference on this. This interests me very much. Yes, yeah.
One more question without the visual aids.
Yeah. Okay. I'm going to see if I can disconnect myself. Yeah.